I present a survey on compressive sensing of low-rank matrices. It's some survey on recently developed algorithm for this very hard problem. We will think about an inverse problem where we'd like to reconstruct a known low-rank matrix X0 from its linear measurement given by B is A X0, where script A is a linear operator between two vector space C to the n by n matrices, and C to the P is some Euclidean spaces with the dimension P, and the linear operator consists of inner products with P matrices. This is called as compressive sensing because the linear system is underdetermined in the sense that the number of equations is less than the number of unknowns. And it is called as sensing as a generalization of sampling. Let's see some interesting applications that can be categorized as compressive sensing of low-rank matrices. First example is Netflix price. It's a competition for the best collaborative filtering. So they are giving some training set. It is a subset of matrices consists of ratings between users and movies. They are providing a matrix with 480,000 users and 17,000 movies, but they are only providing 1.18% of known entries. And the challenge is how to complete this whole matrix. It is to provide some appropriate recommendation for each user, provide some personalized recommendation system. Often the matrix is assumed to be of low rank because the rating is determined from a few factors. Another interesting example is the study done by Bo Zhao in UIUC. So he considered the reconstruction of dynamic MR imaging. It is a spatial temporal signal, and by the spatial Fourier transform, we can consider the signal in KT domain. And where is the matrix? We are considering matrix problem. So to find the matrix, we apply the sampling in KT domain. First, we sample along time axis. There are capital N frames. When time is t sub k, we have a frame. Then by the Nyquist rate, we are considering the samples, and we stack them as a column vector of length capital M. Then the matrix consists of the n columns of length M. It's m by n matrix. The goal is to complete S from subset of entries. Why do we reconstruct it from the subset? So the motivation is if we can reconstruct the signal from small number of measurements, we can get higher resolution or faster acquisition or both. Then we need to think about why this matrix has low rank. It is due to the partial separable model proposed by Professor Jifei Liang in 2007. The signal is decomposed as summation of product of two separable functions. The first function is only dependent on k, and the second function is only dependent on time t. So if we apply this model to the matrix is factorized as n by L matrix times L by n matrix. The rank is bounded above by the number L. And Professor Liang suggested that for ML application, the number of L of 10 to 15 is enough for a good reconstruction. That means the matrix can be considered as of low rank. The matrix completion refers to the problem described in this framework. Usually we assume that the rank of the unknown remains as a constant regardless of the size of the problem, and the linear operator is given as sampling on locations given by a subset omega. Omega is a subset of all indexes, and the linear operator described as some inner product with some spiky matrix. There's only one and others are 0. related applications are as we saw, collaborative filtering, dynamic MRI application, reconstruction, sensor array localization, and low-order system identification. But I mentioned that we are not considering compressive sampling. We are considering compressive sensing. So there should be some applications where the linear operators is different from sampling. So there is such an example. So the linear operator consists of random ensemble. So actually, if the linear operator is IID Gaussian ensemble, this is well-studied prototype example for developing theory and algorithms for compressive sensing of low-rank matrices. And another related application is apply the idea of low-rank compressed sensing to quantum state tomography. It has been studied by David Gross last year. In order to solve the inverse problem, we need to formulate the problem. There are two different approaches. The first option is to formulate the problem as rank minimization when there is no noise in the measurement. So among all solutions to this linear equation, we'd like to find one that has the lowest rank, that is, minimize the rank over all matrices in this affine space determined by the affine constraint. When there is noise, so we need to allow certain perturbation in the measurement, then the constraint set is given as an ellipsoid. Unfortunately, this problem is known to be NP-hard, so people should have found some clever way to solve the problem. In 2001, Marion Fazo proposed a method called nuclear norm minimization heuristic. So in order to define the nuclear norm, we need to think about the singular value decomposition of a matrix. It's very basic one. So any matrix can be decomposed, has a singular value decomposition where U, V are orthonormal matrices with singular vectors, and sigma is a diagonal matrix with singular values in decreasing order. So without loss of generality, we assume that so X is a tall matrix. Otherwise, we can apply transpose. And we consider a vector that is vector of diagonal entries of the capital sigma, that is the vector of a spectrum of the matrix X. And rank is defined as the number of non-zero singular values that is equivalent to the L1 norm of the L0 norm of the spectrum. Nuclear norm is defined as the summation of all singular values that is equivalent to the L1 norm of the spectrum vector. So from the study on compressed sensing of sparse vector, it is known that minimizing L1 norm induces sparse solution. In this line, we can expect that if we minimize the nuclear norm, that will induce low rank solution. Nuclear norm minimization is just minimizing the nuclear norm under the same constraint set given by the rank minimization. Actually, nuclear norm is a valid norm that satisfies all axioms for the definition of the norm. Therefore, it is a convex function. So this problem is now a convex optimization problem. There is a beautiful theory to solve the convex optimization. There is a good news. So in 2001, Marion Fazo called this approach as nuclear norm heuristic because at that time there was no performance guarantee. So it was a good heuristic at that time. But after that, in 2007, Rehut and Fazo and Parillo have proven that for some good linear operators, actually nuclear norm minimization is not a heuristic. It is guaranteed to work. So it's quite some vague statement. So what do you mean by good, or what do you mean by guarantee? So we need to qualify the statement. First, how do we find a good linear operator? So rank restricted isometric property is a sufficient condition to determine a goodness of a linear operator. Actually, a linear operator is said to be a restricted isometry if it preserves the norm of matrix for every matrix with rank n most R. So how can we interpret this complicated equation? It says that the self-adjoint operator A star A is almost perturbed identity. It's quite close to identity. Actually, the perturbation is bounded by some small constant delta in its operator norm computed over all rank R matrices. And they have shown that there exist many linear operators satisfying this property. One example is, as I told you, prototype example, IID Gaussian ensemble. So let's see how the operator A star A act on a row rank matrix. Here, X0 is the full letter image, UIUC, and its rank is just 3. If you apply some IID Gaussian ensemble and apply its adjoint operator again, we will get this noise image. Although there is some additive noise, we can still read 4 letters from this figure. That means that the self-adjoint operator A star A acts like a perturbed identity on the row rank matrix. When is this property satisfied? For that, Racket and others and Candace and Plan studied the requirement on the number of measurements. When the number of measurements P is proportional to Rn log n, or P is proportional to Rn, then the Gaussian ensemble satisfies this property. Now it's time to clarify the statement of the performance guarantee. The performance guarantee is described by this somewhat complicated inequality. So let's read it one by one. So X0 is unknown low rank matrix, and X hat is estimate of X0 given by certain algorithm or method. For example, nuclear norm minimization. X0, R is best rank R approximation of X0 in probability from the nearest matrix to original matrix X0. Then the left-hand side denotes the distance between the true solution and estimated solution in probability norm. Then the start term measures the deviation of X0 from X0R. If the rank of X0 is R, exactly low rank, then start term vanishes. And the epsilon is the energy of the noise. If there is no noise in the measurement, of course, epsilon is 0. In particular, when X0 has exactly low rank R and there is no noise, the performance guarantee implies that X0 is X hat. That means perfect reconstruction. For example, for the nuclear norm minimization, if linear operator satisfied RIP of order 3R, then nuclear norm minimization provides performance guarantee. Then it remains to how to solve the problem. So we know that it's a complex optimization, so which algorithm do we need to use to solve the problem? The first approach is done by Fezo and Ray Fazzarillo in 2007. It motivates from the computation of the nuclear norm. So actually, nuclear norm is the dual norm of the operator norm in matrix space. So by using the variational principle, we can write nuclear norm as the maximization problem. And the norm constraint, unit norm constraint, is rewritten as some semi-definite constraint. And if we write Lagrangian dual of this problem, it can be written as a minimization problem. Because the problem is convex, there is no duality gap. So nuclear norm can be computed by this minimization problem. If we plug in this to the original formulation, because double minimization commute, so we are solving minimization over 3 variables, x, w1, and w2. This is convex optimization. Actually, it is of a particular kind named semi-definite programming because there are 2 linear constraint and linear objective function, and there is semi-definite constraint. So there exists interior point method in polynomial time, but it's not practical because it cannot solve large problems. Yes, interior point is not scalable. So another people, Kai, Shen, and Candace, thought of another efficient way to solve nucleon minimization. The idea is regularize the nucleon minimization with squared Frobenius norm, like this, with some parameter tau. If we solve the problem, we can obtain the minimizer indexed by tau. They have shown that as tau goes to infinity, actually its intuition is that as tau goes to infinity, the second regularization term can be ignored. Then it reduced to the original nucleon minimization. Then actually x tau converges to the solution to the original nucleon minimization in Frobenius norm. And singular value thresholding is indeed an Uzawa algorithm on Lagrangian dual problem. It is gradient ascent on Lagrangian dual. Why is it ascent rather than descent? Usually we consider gradient descent because Lagrangian dual is concave maximization problem. It should be gradient ascent. So it repeated update given in these two equations is very simple. In particular, the tau denotes singular value thresholding operator. It is just subset thresholding on the spectrum of matrix X. The problem here is the tau, the regularization parameter, and the step size eta k are not specified. So there is no theory how to find appropriate value for them. And the SVT update is only available for the noiseless case. If we consider some ellipsoidal constraint, then the algorithm has higher complexity. It's no more thresholding. The second formulation to solve the inverse problem is named minimum rank approximation. In this formulation, we exchange the role of the objective and the constraint in the rank minimization. Here, the rank plays as a constraint set, and we are minimizing the inconsistency in the measurement with L2 norm. Depending on the interpretation of this constraint, there exist various algorithms, and there is one criticism in this approach. We need to know R in advance. But if we look into this formulation, as we increase R, the constraint set gets larger. That means the minimum is decreasing. There is some monotonicity in R. So by using this monotonicity, we can use bisection search. It will increase the complexity by factor of log R. And usually, in many applications, we assume that R remains as a constant, so it's not a big deal. So we can solve this problem. The first algorithm is Admira. It has been proposed by myself and with my advisor, Professor Yoram Bressler. It has been inspired by analogous algorithm for vector problem, COSAMP, proposed by Nieder and Traub and pursued by Wady and Augusta Milankovic. So here we interpreted the rank constraint in this way. First, we consider truncated singular value decomposition. It's a compact singular value decomposition without considering any zero singular values. Then we take the left eigenvectors and right eigenvectors and consider their outer product. Outer product of two vectors has a rank of 1. And actually, this matrix is spanned by these three rank R matrices. And we called it as an atom. And once we specify this subspace spanned by rank 1 matrices, then problem becomes easy. So minimizing quadratic function over a subspace is a simple least square problem. That's the intuition. The goal of this algorithm is iteratively update the subspace. The algorithm looks somewhat complicated, but there are some important points. Most of the computation is singular value decompositions and least square problem. Given rank R estimate of X hat and subspace spanned by our atoms, we will add 2 or more atoms computed from the image of the residual B minus AX hat by the map A star. Then we consider a larger space because we are minimizing the cost function over larger subspace, including the previous estimate X hat. It is quite natural that the cost function is decreasing. After that, to satisfy the rank constraint, so we need to reduce the rank. It can be done by singularity composition, but by help of restricted isometric property, so we can achieve net decrease of the cost function by this iteration. The second algorithm is named singular value projection, proposed by Mekar and his collaborators last year. It has been also inspired by analogous algorithm for vector problem known as iterative hard thresholding. Before we describe this approach, let us get a short review on projected gradient descent in convex optimization. The problem is minimize convex function over a convex set. So we can do that by this iterating this update. We move the variable along negative gradient with some step size eta t, and in order to satisfy the constraint, we project back to the constraint set C. It is known to converge to the global optimum by appropriate choice of step size. It is practical when the set admits an efficient projection operation. So let us compare the framework of projected gradient descent in convex optimization to minimum rank approximation. So what was our objective? It is just quadratic function that is convex and differentiable. It's a very nice function. How about the constraint? Unfortunately, it's not convex, but it still admits an efficient projection by singular value decomposition. That's the idea. Although the problem is not satisfying one of important property, we can proceed anyway using the same algorithm. Singular value projection is just a projected gradient descent with step size given by eta is 1 over 1 plus delta. Delta is the RIP constant, and one drawback of this algorithm is for a performance guarantee. So the step size should be given in this way, but computing the constant is another NP-hard problem. It's the drawback of this approach. The third one is power factorization, proposed by Justin Harder and Diego Hernando in UIUC. So they interpreted the rank condition by matrix factorization. So here there is no constraint but the dimension. Only dimension is concerned, where U is n by R and V is n by R. By this factorization, X already satisfies the rank constraint. Then the problem reduced to unconstrained by convex optimization, and they use alternating minimization to get a local minima. It's very efficient algorithm. The next one is OptiSpace. It uses another some bizarre factorization of low rank matrix by Grassmann manifold. So in order to understand their factorization, let us review some truncate singular value decomposition, U, sigma, V transpose. If we think about any rotation or unitary matrices, so R1, R1 transpose is identity. There is no change if we insert identity matrix between U and sigma. Then let us think about utility as product of U, R1. Then here the key point of this decomposition is they are concerning the left and right spaces. Because U and utility spans the same subspaces, then they construct an equivalence class under rotation. Then actually Grassmann manifold is just a set of all R-dimensional subspace of R to the M. So if we say the matrix U lives in the Grassmann manifold, it implies that U stands for any orthonormal basis for the subspace spanned by U. Then the rank constraint can be interpreted in this way. X is decomposed as U, S, V transpose, where U and V are elements of Grassmannian manifold, and they are actually stand for the equivalence class that include U and V. And in this factorization, S is no more diagonal, and there is no constraint on S. Actually, OptiSpace solves the matrix completion problem where linear operator is sampling, and B is given as the sampling of the true matrix X0. They defined objective function over product of two Grassmann manifolds. And this definition of the objective function involves unconstrained least square. It can be solved efficiently, and actually we can even compute the gradient of FUV over Grassmann manifold. Then they did optimization over Grassmann manifolds, and the algorithm consists of two steps. First, guess a good initialization and do gradient distance search on Grassmann manifold. The last one is the most recent algorithm proposed by Dr. Wei Day and Professor Urquiza Milenkovic. They defined the success in a different way. So their goal was to find a matrix that satisfies the rank constraint and they are consistent in the locations omega. Then they use a decomposition with a single Grassmann manifold. Their decomposition is UV transpose, where U is inside the Grassmann manifold, and there is no constraint on V. Similarly to the OptiSpace, the objective function involves the least square problem. It is easily solved, and we can compute gradient. And they did optimization over Grassmann manifold. The novelty in their approach is to define the barrier that blocks to find the global minimum. So they propose a scheme to detect such a barrier, and once the barrier is detected, they did subspace transfer to avoid the local minima. So their goal is to find the global minima for the minimal rank approximation problem. Now let us compare the introduced algorithms. Here, IPM-SDP stands for interior point method for semi-dependent programming for Euclidean minimization. Except the first one, all the other algorithms are highly scalable because they involve only singular value decomposition and unconstrained least square problems. And about the performance guarantee, if there exists rank-restricted isometry for the linear operator, the first four algorithms has performance guarantee. Among them, singular value projection can be thought as best because the required condition is the weakest one. And for the matrix completion, unfortunately, this sampling operator doesn't satisfy RIP, but with additional constraints, namely incoherence, the Euclidean minimization and OptiSpace derive the performance guarantee for this matrix completion problem. But although there is no performance guarantee for matrix completion, the other algorithms, Admira, SVP, power factorization, and SAT, work well for matrix completion empirically. And there are two more points. When they are successful, we want to compare the convergence rate of the algorithm. Admira has the best convergence rate because it converges within a finite number of iterations that only depends on the rank of the solution. And the next one is singular value projection. They have geometric convergence, and there is no explicit guarantee for the other algorithms. And the drawback of SVT and SVP are there are some unspecified parameters for performance guarantee. We can run the algorithms anyway, but we cannot say that by given parameter, we don't know whether the performance guarantee can be obtained or not. There is another empirical comparison of the algorithms provided by Dr. Wei Day. It is from his paper with Professor Urquiza Milenkovic. And he tested the algorithms on 50 by 50 random matrices for consistent completion. And the key point here is the condition number of the random matrix is non-trivial. It can be large. And if we look the result, in higher sampling rate regime, Admira is the best because here Admira set and power factorization show similar performance, but there is some miss, even though the sampling rate is high for set and power factorization. But for lower rate regime, absolutely set is outperforms the other in an impressive way. Unfortunately, OptiSpace wasn't successful in this experiment, but that is because it is very sensitive to the condition number. That's the reason why we used some tested bed with a non-trivial condition number. But to be fair, I need to mention that they resolved this problem by proposing incremental OptiSpace, and which obtained robustness against the condition number at the cost of losing performance guarantee. It is no more guaranteed algorithm. Oh, I forgot to mention that among these algorithms, 3 of them are developed in UIUC. We have quite contribution in this field. So what was ideal in the success of compare sensing of low-rank matrices? We need to think about some properties of the quantities used in algorithms and theory. We use the rank, Euclidean norm, and probability norm. They are all determined by spectrum and unitarily invariant. That means if we apply any rotation, it preserves the quantity. And we often used the best ranker approximation in probability norm. As an optimization problem, this is quite challenging. And mostly it can be by convex. But there was some magic. For every matrix, there exists singular value decomposition. That was a magic. And there is an efficient algorithms, power iteration, or QR, LU. So we can already compute the decomposition in an efficient way. And there is more. Mirsky have shown that singular value decomposition provides the best ranker approximation in any unitarily invariant norm, and depletion, that is computing ranker components one by one, can be optimal. Let's twist the problem a little bit. Then we can observe that the problem becomes very challenging. The first variation is robust PCA proposed by John Wright and Ima. And they consider the problem where matrix is corrupted by additive sparse error. Then it can be considered as matrix completion with some peculiar norm that is not unitarily invariant, but they proposed a clever way to solve the problem, and they fully characterized the behavior in theory only for the noiseless case. Another variation is sparse PCA. It's decomposing a symmetric matrix like eigenvalue decomposition, but there is another constraint on the eigenvector. Eigenvectors should be sparse. But although we are still using low-rank approximation with respect to probability norm, we are working in Hilbert space. But because we have added one more constraint, some peculiar constraint, the problem becomes extremely difficult, and there is a limited theory about this problem. So that's it.